Okay, so many thanks, Shubhajit, and let me start with my final lecture. So today we will go back to the model of learning under group invariances under the latent action of group symmetries, and in the second lecture we sort of discussed this problem at a high level, and we discussed it, for the action of general groups, and we discussed some general results pertaining some general results which connect this problem to invariant theory and transcendence degrees. So today we are going to take a more pedestrian approach, and although this lecture is going to be about the model of learning under group invariances, is not going to be a continuation of the second lecture, so you can also enjoy this as a standalone lecture on its own. So today we are going to take a more pedestrian approach, and we are going to take some relatively simpler sort of sub models or settings of this problem, and we are going to go into some more mathematical details and see how exactly the group invariances come into play when you try to understand fundamental properties of this model. So today we are going to discuss about the information geometry, so to speak, of learning under group symmetries. So please stop me and point out if something is not legible or if something is not clear when I speak, and so on. So information geometry of learning under group symmetries. So we will come to exactly what we mean by information geometry. But let me start first with by reminding you of the basic model. So basic model. So you have observations yi of some signal theta star in RP, and you observe it with noise xi. So xi's are, and today we are going to use the scaling where the xi's are IID normal, standard normal in p-dimensional space, and sigma is noise level. Okay. And this G is GI, so the xi's are IID. And these GI's are group actions, so imagine they are rotations. So GI's are IID following the Haar measure on some compact group G. So compact group, G is a compact group, which is a subgroup of the orthogonal group in p dimensions. Okay. And let us also remind ourselves of some basic examples we discuss. So for example, we can think of a bag of numbers. So you have a bag of numbers. So these are just some integers or some real numbers. And you do not really, we are really interested in what the elements. So we are really looking at this bag of numbers as a set, but we are only able to take measurements as a vector. And every time you take measurements, the numbers are permuted in some way. And what we are interested in is to find this set of numbers, this unordered set of numbers. Okay. So there, G is the permutation group on P elements. Then we have the model of multi-reference alignment. Or the so-called MRA model. So here you have you think of a function or a vector living on the discretized circle. So there are p elements here, and we will view it as z mod pz. So this is a function from, or let's say theta star. You can view it as a function from z mod pz to reals, and every time you take a measurement, take a noisy measurement of this, your function gets rotated by an unknown amount, which is reflected in this GI. And the group of rotations is here in this problem is just z mod pz. Okay, this is z g equal to z mod. So this is a nice finite abelian group. Okay, so this is the setting on which we are going to focus the most in today's lecture, because this is finite, this is abelian, and basically you cannot get any simpler than this. And the third example, just to remind you, and for those of you who are here in the second lecture, just to remind you, and for those who are new, just to lay out the sort of the panorama of settings which this model covers. So rigid body learning. So basically, you have a complicated rigid body consisting of n particles in RP. So the way you can think of it is that, okay, so let's call this, for reasons of clarity, let's call this Rk. So each of these n particles is represented by a vector in Rk, and we line these vectors up as the columns of a matrix. So this matrix is K cross N. And then we take noisy observations of this rigid body, and every time this rigid body is measured, its image is taken, it gets rotated by some unknown amount, by by a rotation, by a, let's say, an element of the orthogonal group in k dimensions. So the elements of G are acting on the columns of this matrix as orthogonal matrices in k dimensions. Okay, so G is equal to S of k. Okay. By the way, if there are any questions, please feel free to stop me and interrogate. And some natural or easy observations. So observation can only recover the true signal up to its orbit, which we call O theta. Orbit under the action of G. Okay. So this is a basic feature of this problem, and so just for someone who might be confused, so O theta is equal to theta in RP, such that theta is the shift of theta star by for some G in the group of indexes. Okay. And the other setting, which the other property, which is going to sort of become important later, is that sigma is large. So, for instance, for theoretical analysis of this model, a popular regime is when every other parameter of this model is kept fixed, like P and the signal space and even the number of observations, and we are really interested in the behavior of the model when sigma goes to infinity. So that's the most important regime. So the point is that the behavior of this model when sigma is low versus sigma is high is very different. Or when sigma is low, this is like this behaves almost like a Gaussian standard Gaussian estimation problem. So it is as if for important properties of the model, it is as if the group rotations do not matter. But for sigma large, this is not the case, and the presence of this latent group action plays a very important role in determining fundamental features of this model, including in particular sample complexity. Okay, and what is the likelihood function of the model? So this is just if you sample this model, if you sample a y from this model, what is the probability or the probability density of getting the observation y? And this is, I will write it in two ways. So first of all, if we knew what G was, so if we knew what this G was, then let me write that first. If we knew what this G was, then it is just the probability density which is induced by the Gaussian noise. So this times exponential minus y minus g theta star square, this is L2 norm, divided by 2 sigma, right? This is if G was known, but G is not known, and in fact G is drawn uniformly at random according to the Haar measure on the group script G. So we have to average over, okay? And EG is always expectation with respect to G following Haar measure. So it is the uniform measure on the group script G compared. And in the setting of key importance to us, if G is finite, then this is 1 over cardinality of G, and then G in script G, this quantity. Okay. So far so good. And let us remind ourselves what was the problem. What was the problem caused by the presence of these group actions? So this is a fundamental problem in this model, which is that so the standard statistical techniques usually rely on averaging to kill off the noise. So for example, if these GIs were not present, this was always identity, then you could take a bunch of these YIs and average them. And by the central limit theorem effects, if n was sufficiently large compared to the noise level sigma, the contribution from the noise will be of a smaller order compared to the strength compared to the size of theta star, and that will basically help us recover theta star. But here, averaging does not work. And this can be seen from this simple example. So suppose we are on this circular model, and the group is just SO2. So these are rotations on the circle, and you have some function which is living here, let's say. So in each observation, you get sort of shifted or rotated versions of this function. So if you average a bunch, if you take many observations like that and average them, what will happen is that the noise will be killed off by central limit theorem effects, but here you will get an average of GI theta star I equal to 1 to n, and this will just appear as a constant blur. It will appear as a constant value all over this circle, where the common value will be just the average of the coordinates of theta star. So this is just a constant. So this is not really informative. So this is the problem. And then we discussed what were the so this shows that standard ideas might not suffice. So we take a step back and try to understand what are those objects or what are those functions which we can actually effectively estimate using classical methods. And we soon realized that if you take some function, f, which is invariant, f is invariant under the action of G. So for example, f of G times theta, G acting on theta is equal to f theta for all G in G. Then we are good, because then even if you act on the function by your group, the theta star might change to G theta star, but the value of f remains the same. So if you apply f on your shifted function and take the average, roughly speaking, you should get many noisy observations of this same object, and so the standard statistical technique should work. So these are good functions. So this can be effectively learned. And now, so and the natural question is, what kind of such what are such classes of functions? So, for example, again, let's go back to our examples. So, of course, the class of invariant functions is dependent on the group G. So, if let's go back to our examples, and the basic example of a bag of numbers, if G is the group of permutations, then, for example, you can take f of, and let me write this as theta 1, theta 2 up to theta p, and this is just theta I to the k. Okay, I equal to 1 to p, and k is bigger than equal to. Okay, so the moments are conserved, and basically, this actually for the permutation group, this gives you an algebraic basis of all invariant functions. So that's this kind of Newton's theorem. But you know, so we are, for the moment, we are just looking at some examples. So these are some clear examples. For G is equal to Z mod PZ, which is the MRA model, multi-reference alignment model. The same examples work. So these are so summation theta I, okay, I equal to 1 to p. And actually, it is easy to see that you can get other classes of invariant functions which are new, which are not covered by the permutation example, and which are not also sort of generated by these moments. So for example, you can take any function of successive pairs of points, and if you average successive pairs of coordinates, and if you average or if you sum over the entire group, like here we have theta j plus 1, and you sum over j in Z mod PZ, then this is going to be invariant, right? Because it preserves the order, preserves pairs, successive pairs. And clearly there could be more. So one observation here is that the group of permutations is a big group. The group of cyclic, this is Z mod PZ is a group of cyclic permutations. This is a much smaller group. And smaller the group, the bigger the class of invariant functions. And bigger the class of invariant functions, you can think of, so suppose I am able to estimate this some invariant function well. So suppose for f, my estimated value is f hat, okay? So I can set this equation. This is not exactly true, there are some errors, but I can set this equation, and for each invariant function, I can have one equation like this, right? So the point is that the more invariant functions are there, the more equations I have, and the easier it is to estimate. So this ties in with the fact that if the group of invariances is smaller, it's a simpler problem. It's actually closer to the classical Gaussian estimation problem, and the group is just identity. And the easier it is to estimate the function. Whereas bigger the group of invariances, smaller is the ring of invariant functions. So we will have less number of independent equations, and therefore it is harder to estimate the truth star. And okay, but the fundamental question is whether we will be able to. So how far can we get with these invariant functions? Can we go with invariant functions? So this is a fundamental existence or identifiability question. So even without noise, if I was actually given the values, true values of these of all these f theta stars for all invariant functions f, does that uniquely determine theta star? Because if that is not true, then the approach via trying to understand only invariant functions is not going to work, because there is no identifiability. And to the answer to this question, as we briefly alluded to the previous day, is yes. So the answer, so this is a question, and the answer is all the way. And the mathematical statement is that if you look at R x, so R x1, x2, xp, so this is the ring of polynomials in p variables, and we look at superscript g, so this is the polynomials, ring of polynomials in x1, x2, xp, such that they are invariant under G. Okay, so this is the ring of invariant polynomials under G. So, for example, in these examples that we saw, all the invariant functions that we have considered are actually polynomials. So these are in fact invariant polynomials, and this identifies the orbit of theta for all theta. Okay. So this is a basic existence result. So without this result, invariant functions won't suffice to understand this. So we skipped over the proof in the previous lecture, so let us do it this time. So suppose scripto of theta 1 and scripto of theta 2 are two orbits of G acting on RP. Okay. Now, the point is that if there is some intersection, so if theta 1, if the orbits of theta 1 and theta 2 intersect, then they must be equal. Because basically, if there is a point, so suppose this is one orbit, this is another orbit, and if you have a point of intersection, then by definition, you should be able to generate any orbit by starting from a single point in that orbit and then moving that point around under the group action. So if two orbits intersect, then you are basically, these two orbits have to coincide. Okay. So therefore, if these are two, therefore, if they are not the same orbit, then their intersection must be empty. Okay. So maybe we just use this one. So from here to here. So now, So we have two disjoint orbits, and since G is a compact group, therefore these orbits are compact sets. Okay, so these are compact sets in R to the P. And by Urysohn's lemma, so this is O theta 1, this is O theta 2, and by Urysohn's lemma, these are disjoint compact sets. There exists a continuous function such that f is identically equal to 0 on the first orbit and f is identically 1 on second orbit. Okay. Now, so far so good. We have distinguished these two orbits by a function, but this is merely a continuous function, which is a much larger class than polynomials. So we now want to get from continuous function to polynomials, but this is not difficult because we can put this these orbits under some compact set, and on this compact set, on K which is compact in RP and containing both the orbits in their totality, we can apply Stone-Weierstrass theorem, Stone-Weierstrass theorem to get Stone-Weierstrass theorem to get polynomial Q such that Q is less than equal to, so Q approximates F in the L infinity norm of K to a degree 1/3, let's say. So L infinity norm on the set K. Outside K, what happens? We don't care because the orbits are fully contained inside. So therefore, this implies in particular that Q is less than equal to 1/3 on the orbit of theta 1, and Q is bigger than equal to 2/3 on the orbit of theta 2. So we now have found a polynomial which separates the two orbits. And we are almost there except for the G. So we need an invariant polynomial that is invariant under the action of G in order to which separates these two orbits, right? Because invariant polynomials are the ones which we are able to handle well and which we like in this one. To this end, so to go from some polynomial Q to an invariant polynomial Q that separates the two orbits, we use the so-called Reynolds operator, which we also briefly introduced in the previous lecture. And this is simply the expectation of Q of G acting on theta, where G is drawn, sampled from the Haar measure on the group. So this, if you think of it, is actually a polynomial Q tilde of theta. And because, so if you look at this expectation as a function of theta, it is a polynomial, basically of the same degree as Q. And because of the way it is defined by averaging over the group G, therefore Q tilde is almost by definition an invariant polynomial, a group G invariant polynomial. Now, the orbit is invariant under the action of G. The Q, the object inside the expectation, is always less than equal to 1/3 on the orbit of G, on the orbit of theta 1. So therefore, when you average over the orbit of theta 1, all the time this will be smaller than 1/3, and therefore this average value is also going to be smaller than 1/3 when theta belongs to the orbit. So Q is less than equal to 1/3 on orbit of theta 1, Q tilde, and similarly greater than equal to 2/3 from the orbit of θ2. And Q tilde is an invariant polynomial which separates, therefore separates the two orbits. So indeed, this proves the existence result that the basic existential question that the invariant functions indeed suffice to identify the true signal θ star, or at least its orbit. Okay, but this, as you noted, as you might have noticed, it's a deterministic theorem. I mean, never mind this expectation. This is, if it is a finite group, this is just no average, right? This is really a deterministic theorem. This is a basic identifiability question for the model. We do not really have any noise here. Whereas the true model, when there are noisy observations, incorporates noise, and therefore that's the next key issue we are going to discuss. So let me retain the model and erase these other things. So let me now introduce some basic objects related to this model. So we have already introduced the likelihood, and this you can actually consider for any theta. You can think of this as a function, and then it's of theta, and then you can write this as a function for any theta. So we will do that. So if you have observations y1, y2, capital Y1, Y2 up to capital Yn, then your probability is the product of p theta, and you are coming from theta. So let's say probabilities are maybe p theta star I equal to 1 to n, and it is we want to maximize this likelihood under theta star. So the natural so the equivalent way people like to think about is that you take the negative log likelihood, and you want to maximize this, so you want to minimize the negative. Okay, so this is and you want to take an average, maybe doesn't matter, it's a constant for this purpose. Okay, so this function, so now we can think of this as a function of theta star, and this function is theta. You can think of theta star to be varying, so this is, we consider it as a general function of theta, is the so-called empirical risk, and it concentrates, as you might imagine, for large n around its population version, which is r theta, which is just minus expectation log p theta star p theta of y. Okay, the expectation is now with respect to both the noise and the rotations. So these are some generalities, and it is known, and actually it is a simple computation which we will not have the time to do in detail, but it is known that r theta, so suppose your true function, so suppose your true value of theta, the true value of your signal is theta star, and then you sample observations from theta star, and then you look at this function for a general theta. So expectation with respect to p theta star. Okay? But inside you vary theta as a general quantity. So this is just d, is the Kullback-Leibler divergence of p theta star with p theta. And I will define the Kullback-Leibler divergence very soon, minus expectation of log p theta star y plus or constant. So basically, the negative log likelihood is basically closely related to this Kullback-Leibler divergence between p theta star and p theta. And this is a good point to define the Kullback-Leibler divergence between two densities p and q, which is essentially integral p y log py by qy. So the Kullback-Leibler divergence is a famous quantity. It's almost a metric, but not quite. There is no symmetry, but it has many other good properties. And in particular, this identifies the distribution. So this is zero only if p theta and p theta star are the same, and which under identifiability, it means that theta and theta star must be the same. So this to be zero. Okay. And let me now introduce. So these are all standard theory. There is not much to worry about. So let me retain this and remove these other parts. So let me now. So we are close to the end of the cast of characters that we are going to introduce, but please bear with me and introduce one of the last ones. So this is the so-called Fisher information matrix. So Fisher information matrix. And this is essentially I theta is equal to expectation minus, I will come to what this is, log p theta y. So this is essentially, so this is just the second order derivative of the population risk. Okay. So this is the Hessian of risk r theta. Okay. So this might sort of look too many functions and too many objects at one go, but let me now state a classical result which actually justifies why this is interesting. So for that, let me introduce the MLE. So this is the maximum likelihood estimator. And this is just the argmax of theta such that which maximizes the likelihood, which is exactly the argmin Rn theta. And this is more or less r theta, as we have discussed. So this is the maximum likelihood, and it is known that theta hat MLE converges to theta star in an appropriate metric, because here we can identify only orbits, not individual signals, but basically you look at the orbit of theta hat MLE, and this is the orbit of theta star. So there must exist some point in the orbit of theta hat MLE which is actually close to theta star in Euclidean distance. So that's the interpretation. But let us not worry about this in the limited span of one lecture. So this converges to theta star as n goes to infinity in an appropriate sense and metric. And under these conditions, there is a classical theorem which tells us that square root n, where n is the number of observations, times theta hat MLE minus theta star, converges in distribution to normal with mean 0 and variance, which is the Fisher inverse of the Fisher information. So it's the Hessian of the population risk, Hessian of the risk r theta inverted. That's the standard error. So what does that mean? Implication. This means that roughly speaking, theta hat my MLE minus theta star, and in that sense, in that metric. So, and let us not worry about the metric and just take Euclidean norm. So this is, remember that this is the variance, so this is the square. So this is like this is something like the size of this I theta inverse squared, so in an appropriate norm, divided by n. Okay. So basically, if this has to be small, then n must beat the size of the inverse Fisher information. And we are interested in the regime when sigma goes to infinity. So if noise level is high, we want to understand how big we need to take n compared to sigma, so that this approximation is good, this mean squared error is small, and we have found the answer here, which is that if you could estimate if you could understand the size of the inverse Fisher information matrix, which is the size of the inverse Hessian of the risk, then n has to be basically large enough to beat that in order for the mean square error to be small. So this is going to dictate to us the sample complexity of the problem in terms of the noise level sigma when sigma goes. So the point is that all that this has done is that it has reduced us to the situation of trying to understand. So remember that this Fisher information matrix or the population risk r theta, these are like intrinsic properties of the model. These are not empirical quantities. So we can just forget the sort of the GIs and just look at the basic stochastic model, y equal to g theta star plus sigma xi, where xi and g are independent. G is uniform R from the group G, and xi is normal, standard normal in p dimensions. Then what is the behavior of the inverse Hessian of the risk near theta star? Okay, so remember that we are supposed to look at it near theta equal to theta star, and because of this identification, when we try to calculate the Hessian of this quantity near theta equal to theta star, this everything else doesn't depend on theta. So we really are interested in the Hessian of the Kullback-Leibler divergence of this model near theta equal to. So I hope I have convinced you that what we are really interested in is the behavior of the Hessian of the Kullback-Leibler divergence, Hessian of the Kullback-Leibler divergence between p theta star and theta at or near theta equal to theta star. Okay. So this is what we are interested in. And to this end, let me write down. So I think by now probably you are familiar enough with this model. So let me erase the basic model and create some space, or maybe I can just write it here. So let me write down an expansion the Kullback-Leibler divergence near okay. For us, it will be effective near theta equal to theta star. So let's say, suppose theta phi belong to RP. Okay. So this is just a general theorem about the Kullback-Leibler divergence of this model. And suppose expectation of G theta is equal to expectation of G phi is equal to 0. So this is the sort of, this is the first moment. So this is the average of, so if you were doing cyclic shifts, this is just the average of coordinates. So this is just a normalization. And then and some okay, some other bells and whistles like norm, like sigma has to be bigger than the L2 norm of theta, and your distance between theta and phi has to be smaller than 1/3 of this norm. These are just normalization issues. What we are, so this is going to always hold for the situation which we are interested in, which is that theta, so phi is theta star, theta is very close to theta star, so this distance is very small. So of course this is going to be smaller than the norm of theta. And then sigma, we are interested in the high noise regime, so sigma is actually going to infinity, so of course this is going to be 6. But what is the statement? The statement is that the KL divergence between P theta star and P theta is basically comparable to a series. So C upper bar and C lower bar are universal constants. So I will come to what these quantities are. So this is √3 sigma to the 2m times m factorial divided by, so this is the left hand side, the right hand side is twice the same thing, but only a truncated series of 2k minus 1, and then m factorial. So if you compare with the left hand side, very similar, plus, but here we have truncated the series at k. So for the rest of the terms, we have it's 2 distance, appropriate distance between theta and phi square divided by sigma to the 2k. Okay. And this is just some centering. So there is also a complementary lemma as to what happens if you center. So if theta prime is equal to theta minus its mean, this is the theta prime is the centered version of theta, and similarly for phi, then there is a very clear relation between d theta phi equal to d theta prime phi prime plus 1/2 sigma square, the difference between mean squared. Okay. Okay. So now, what are these delta m's? So technically, the statement of the result is not over. So let me define the delta m's here. Delta m is simply the rotation minus phi. So this is the moment difference tensor. So this is the moment difference. So is it okay to take 5 minutes? Okay. So I'll just state some things and then it will be done. So this is a basic result. And what this tells you is that this tells you that if you look at the landscape of the KL divergence of this model, then these moment difference tensors, they come up in a natural way because of these inequalities, and basically, so you are interested in how the Hessian of this model, how the Hessian of so this is the Hessian of the Kullback-Leibler divergence between E theta star and E theta. So how the Hessian of this DKL, it behaves at theta equal to theta star. So what you really need to do is that, and you are going to invert the Hessian because you have the inverse Fisher information matrix. So you are going to, what we are really interested in is a quadratic lower bound on this DKL near theta equal to theta naught, theta equal to theta star, quadratic lower bound in the distance. Okay, when theta is very close to theta star, because suppose we could show that this function is bigger than or equal to some constant times this distance squared. So when you take the Hessian will, its curvature will be lower bounded by this constant, and when you invert this Hessian, the the inverse Hessian, the operator norm will be bounded by this constant. Okay, and because of the nature of the terms of this series, this constant will depend on sigma, and that will give us an upper bound on the set. So this is the relationship. And let me just close this talk by sort of quickly stating what is known and what is unknown. So theorem. So we are looking at the MRA problem. So G is Z mod PZ. And suppose the signal theta star has full support. Okay. So this is so there is no coordinate which is 0, and in fact all the coordinates are separated away from 0. So then the square root n times the distance between theta hat MLE coming out of n observations, and theta star, this is of the order, this is bigger order than sigma cubed coming out of that pair of inequalities, which is implying that n has to be roughly bigger than of the order sigma to the 6 in order to, so this is the central. And the most interesting situation perhaps is when you have theta is sparse, sparsity understood in the usual sense. So there we can show that sample complexity in the same sense is of the order of sigma to the 4. So if no group rotations were present, it would be sigma square. That's easy to see because of central limit theorem scaling sigma over square root n. Here is sigma to the 6 when support is full. For theta sparse, this is going to be of the order sigma to the 4, which is an intermediate scaling that is not known in any other statistical model to our understanding. And this has two categories or two regimes of sparsity. So for there's a dilute regime of sparsity, which is roughly of the order p to the 1/3. The size of the support is of the order p to the 1/3. And then there is a moderate regime where the size of the support is between log p to the 9 and p over log p to the 5. Okay, so almost going all the way up to linear density, up to logarithmic factors. And here the techniques are Fourier analysis and uniform uncertainty principle. I will be happy to chat with anyone who is interested in this later. And in the dilute regime of sparsity, the techniques are combinatorial. And in particular, they connect to the so-called Beltway problem from combinatorial optimization, which is another interesting Pandora's box. And if anyone is interested in this aspect, I'm also happy to chat offline. Okay, thank you.